Namaste. All right. Good day, guys. Welcome to the apocalypse. It's Mr. Golis. All right. Today's lesson is on energy. Okay. And this is an important topic in physics. Obviously, you know the word. We use it all the time. You say either, I don't have any energy today, or I'm feeling very energetic. What does that really mean when we say energy? What is it? All right. The first thing you need to know about energy is that I can't answer that question. We don't really know. We don't know what energy is in the year 2020. Human beings know it has various forms. It changes, okay, from one form to another. All right, like from energy of motion to sound, like when I do that. Okay, motion, and then it went out as sound. But I can't tell you exactly what energy is. We know that even matter itself is energy. Einstein showed that when he came up with his theory of relativity. But we can't tell you what its base form is. All we know is that it all was created 13.7 billion years ago, seemingly out of absolutely nothing, in an event called the Big Bang, and it's just been here ever since. Okay, so let's go into it a little bit. All right, so what is energy? Again, we don't really know. All right, it has various forms. All right, all right, so one is, you can call it heat. Is a form of energy. This is thermal. All right. Sound. Sound could be called acoustical. There we go. Light is a form of energy. That's radiation. Radiates out, and so on. So these are various forms of it. Okay. What you do need to know, the cardinal rule about it, is that energy is, at least as far as we know in the year 2020, energy is neither created nor destroyed. Right? It can only change form from one to another. Okay. So, for example, when you heat up a log like that, or you have a fire going, all right, it starts to burn. Some of that energy comes off and changes into light. Obviously, you can see the fire, where the light come from. Well, it came from the thermal energy, all right, in the whatever it is that you're burning, and so on. But it wasn't just spontaneously created, okay? It just changed from one form to another. All right. Now, the next statement is something that I want you guys to memorize, and that is what's called the conservation of energy, okay? And that is, energy is neither created nor destroyed. Fit that in there. Okay. You get the idea. All right. That's called the conservation law of energy, and that is a true conservation law. You might have heard in chemistry, your chemistry teacher might have said, well, there's a conservation law of matter. All right. Matter in a chemical reaction is not created or destroyed. But the reality is that's not really true. All right, matter can be destroyed, and that happens in nuclear reactions all the time. When a nuclear reaction happens inside a nuclear bomb or a nuclear reactor, some of the matter itself, some of the mass itself, actually winks out of existence as mass and changes into heat and light, and a lot of heat and light, actually. So conservation of matter is not a true conservation law, but this law, conservation of energy, is. All right, make sure you memorize this. Okay, I don't ask you guys to memorize a lot. You should have this memorized though. All right. Okay, let's talk about the units on energy. How do we measure it? Okay, the units is something called a joule in the metric system, and 1 joule is a Newton times a meter. Again, you know, that just don't ponder that too much. What's a Newton times a meter? I don't really, don't ponder it too much, all right? A joule is defined as a Newton times a meter. That'll become more clear when we do the lesson on the concept of physical work, okay? So there's that. Sometimes you might see energy measured in a calorie, okay? Or another unit, because a joule is actually kind of small and a calorie is kind of small. So sometimes when we want to measure larger amounts of energy, we use what's called a British thermal unit, or a BTU. Okay. All right. All right. So that's how we measure energy. Let's look at different types. And I know on these videos I might be going a little bit fast, but again, just kind of bear with me. I try and keep them like about 15 minutes or so. All right. And I know that you guys can pause these things and scroll back whenever you want. All right. Okay. So we have different types. Okay, and the 3 main types are potential, kinetic, and what's called rest energy. Okay, I'm thinking you guys can see that. All right. There you go. Okay. Okay. Let me go into a little bit more detail. I'm going to start with potential. Potential energy is the energy that an object has by virtue, listen to my language, by virtue of its position. Okay? So it's energy of position. What do I mean by that? Well, let me just kind of illustrate here. Let's say here's the ground. Okay? And here's a ball, and it's above the ground and has some mass. Okay, we would say that if I'm holding the ball there, we would say that that mass has some potential energy. If I let it go, what's going to happen? It's going to fall. All right, it's going to start moving. All right, why? Because it has some energy. Now we'll go into this a little bit in a second, but that potential energy will start to change into the energy of motion, the next type, which is kinetic energy. All right, so let's look at the things that potential energy depends upon. One, all right, let me write them over here. One, it depends on an object's mass. Okay, so here's the ball, and let's say it has a certain mass, but let's say here's another ball, and it's bigger, and this has more mass to it. Which ball would have more potential energy, given that they're the same height above the ground? Well, the one with more mass would. The way you can think about it is like, all right, okay, so if you were laying on the ground and someone was holding a tennis, took a tennis ball, a tennis ball, which I just happen to have in the room, and a bowling ball, and said, which one would I rather drop on your face? The tennis ball? Would you rather I drop on your face the tennis ball or the bowling ball? All right. Any sane person would say, well, it's going to be the tennis ball. Why? Because that potential energy, both objects have potential energy. The bowling ball would have more, and when it impacted with your face, you would definitely, it would transfer all that energy to your face, and you would definitely know it. So more mass, more potential energy for a given height, which is the next factor that goes into potential energy, which is your height above the ground. Okay, so if I back to the diagram here. So here's the ground, here's a ball that's this high, and here's a ball that's this high, and let's say I actually drew them the same size. I'm trying to do that again. Okay, here's ball number one, here's ball number two. All right, ball number one has a smaller height, h. Ball number two has a higher height or a larger height. All right, this ball right here we say has more potential energy. And again, this is common sense. You kind of know this. Again, if someone had to drop something on you, would you rather have them drop it from 3 feet above you or from 30 feet above you? And obviously 3, because if someone dropped something on you from 30 feet, any decent sized object, right, it would hurt more. Why? Because it would give you more of its energy once it impacted you. All right. And then the other thing it depends on is gravity itself. What do you mean by that? Well, back to this diagram. Okay, so let's look at one of these particular masses here. If you're on Earth, where the acceleration is 9.8, that's one thing. But what if I took the same object and instead of having it 4 feet above the ground on Earth, I had it 4 feet above the ground on the moon? And if I let it go on the moon, where the acceleration is something like 1.6, all right, you fall on the moon. The moon has gravity, it just has less gravity. So when you drop something on the moon, it falls, it just accelerates less than on the Earth. And by contrast, if you went to like the planet Jupiter and you drop something on Jupiter where the gravity is about 2.5 times that of Earth, all right, 4 feet above the surface of, well, Jupiter doesn't have a surface, but let's just say 4 feet of height above Jupiter would have more potential energy than 4 feet of height above the planet Earth. Okay? All right, so now we have an equation for this. When you put them all together, and the equation is, we use the variable U, I don't know why, U, for potential energy, and that is equal to M, G, and H, okay? Make sure you know this equation. Again, I don't ask you to memorize a lot, but I think you should know that. Definitely know the factors that potential energy depends upon. All right, the next type of energy is energy that has motion. Any athlete knows this. If you've ever been hit by something, either a person or you got hit by a ball or a puck or something like that, the object gives you its kinetic energy. All right, so let me write that down. Kinetic energy is the energy that you have by virtue of the fact that you're moving. Okay? So, and this depends on two things also. One, it depends on your mass, right? So, no one's afraid of getting hit by the quarterback, but everyone's afraid of getting hit by the linebacker. Why? Because for equivalent speeds, if a quarterback runs into you, that's one thing. But if a 300-pound linebacker runs into you, which has much more mass, you're really going to know it. Okay, so mass is one factor that goes into it. And then the other factor that goes into kinetic energy is how fast you're going. So we're going to say velocity. Okay, so if I take this tennis ball and I kind of toss it at you, and you get hit by it, that's one thing. But if I take the same tennis ball and I shoot it out of the front end of a 155 howitzer at twice the speed of sound, that's a different story. All right, it's going to hurt you a lot more. Why? Because it's going faster. It has a higher velocity. And so the equation for kinetic energy is has these two variables in it, and we give the variable K. So kinetic energy in joules is equal to 1/2 mv squared. It actually depends more on how fast you're going than how big you are, all right? But it depends on them both, okay? The third type of energy that you can have is called rest energy. Rest energy is energy you have just by the fact that you exist as matter, okay? And here's what I mean by that. It depends, all right? If I, let's say I have some kinetic energy because I'm moving. So I have some object and it's moving at some speed v, right? I know it's a little difficult to see, but I'll bring it up to you like that. Okay, and here's some guy, some random guy standing in front of the object. Okay, and let's just give the guy a name, just some random name. We'll call him Mr. Kelly. Okay, and he's about to get hit by this object right there. To him, this object's moving, so it has a lot of kinetic energy. So he's totally going to feel it, and it's going to completely ruin his day. All right. But let's say that there's some other guy, and he's moving with the object. Okay. And let's give him a random name too. We'll call him Mr. Goalless. Okay. And he's moving with the object. Now, if he's moving for the same object, this guy right here doesn't see that it has any kinetic energy because he's moving with it. There's no relative motion between there. So does the object have kinetic energy or does it not have kinetic energy? Well, that's kind of depends on your point of view. But the type of energy that the object would have, no matter who's looking at it, is rest energy. Okay? And that's the third type. And rest energy is the energy that you have by the fact that you have mass. So it depends on mass. Okay? And we'll go into this a little bit more, but rest energy is given the equation E, energy in joules, is equal to mc squared. Okay? And this is Einstein's atomic bomb equation. It comes from his theory of relativity. All right? And what this says is that matter is just a form of energy. It's called the mass-energy equivalency relationship. Say that one. All right? But basically what it means is just that matter is another form of energy. All right? And it can be changed. And again, like I said, when an atomic bomb goes off, some of the mass is actually changed into heat and light, other forms of energy. And it's actually a lot too, because see this number right here, C, that variable stands for the constant, the speed of light in a vacuum. And that's a big number because light goes really fast. It's 186,000 miles every second. Or if you do it in meters per second, it's 3 times 10 to the 8th meters every second. So C squared is 9 times 10 to the 16th. That's a 9 with 16 zeros after it. I don't even know how much, what that number is called. It's 90 gajillions or something like that. But the bottom line is, if you multiply even 1 kilogram by this number, you get 9 with 16 zeros after it joules of energy, which, if you want to blow up a city, that'll do it. If you want to power that same city for 5-6 years or so, that'll do it also. Okay? All right. So anyway, those are your 3 types of energy. All right. Now, to do a quick energy problem, we need to talk about what's called the total energy. Okay. So let me show you. All right. The total energy you have at any point in time. All right. E with, we usually put a little t after it like that. All right, is equal to the potential energy you have at any point plus the kinetic energy that you have at any point in time. And here's what I mean, okay? All right, so let's say, here's a typical energy problem. So let's say that here is, okay, here's like a high place, like a cliff or something like that, okay? And, all right, here's a mass, and here it is. And we're going to look at it at 3 points in time. And let's say that, all right, so up here, right, the mass is not moving. So all it's in, it has no kinetic energy because it didn't start moving yet, didn't start falling yet. But it has potential energy. All right, so what I can write, I'd write the total energy of this object is equal to its potential plus kinetic. And let's, just to give it a number, I'm going to say that these two add up to 100 joules. Okay, so it has 100 joules of potential energy. It doesn't have any kinetic yet. All right, at the top, before it starts to fall, its kinetic energy is 0. Now, we're going to contrast this with when the object falls down. So we're going to look at it right when it impacts the ground, not when it stops, but right the instant upon impact. Now, check it out. It still has a total energy because energy is neither created nor destroyed. Its total energy is still 100 joules, except what happened is that potential energy on the way down was changed into kinetic energy. All right. So as it was going down, the number of joules of potential energy got smaller and smaller, but they got picked up by the kinetic energy. All right. So down here, this energy is still potential plus kinetic, but since the height is 0, since it's on the ground, U is 0 at the bottom, but guess what? K is now 100 joules. Now, again, to kind of compare that to another point, if I take a look at it right here, okay, halfway through. All right, so halfway through, guess how much energy it has? It has 100 joules. But now, because it's still falling, it's got some speed now, but it's not as high, so it's got some kinetic energy, but it's not as high above the ground. It's still above the ground, it's got some potential energy, but not as much as up here. Its potential energy and kinetic energy at a point halfway would be split. So I'd have 50 joules of potential, 50 joules of kinetic, and together they would still add up to 100 joules. And in fact, the total energy, because of the energy conservation law that this object has, the total energy between potential and kinetic is, when you add the two together, is going to be the same 100 joules throughout the entire process. Okay, I think that's enough to start you guys off. I'll do another video giving a couple of example problems on energy, and I'll post that too because I don't want to make these things too long. Okay, all right guys, goal us out.